everyone here for your attention today. My name is Leo. I'm a postdoctoral fellow at the Department of Neurology over at the Health Campus. Part of the Dr. Katie Cross's MD PhD. We're a lab that investigates Parkinson's disease, but more specifically, we're trying to use virtual reality to kind of study the underlying mechanism that is causing gait dysfunction in these patients who oftentimes, if you see them, they're taking shorter steps, slower steps, the balance is a little compromised, and they're always at risk for falls, and we want to reduce falls. Obviously, that's our number one priority. So what we do at over at the hospital is one of the treatments from PD is we could implant deep brain stimulators in their basal ganglia, the source of their problems. And we can stimulate them, and it really helps with the tremors, sometimes with the motor functions, but it doesn't really help improve their gait, the walking function. And we're trying to investigate exactly why. So one way we could do that is to put them in scenarios that they complain about, okay, I'm having trouble doing this and that. And we could actually turn off the stimulators and record out from those deep brain stimulators to study those moments. But for the study that I'm going to show today, we're studying a very particular phenomenon here, and it's called freezing of gait. So when some of the patients, not all PD patients, when they're walking in the real world, suddenly they're unable to take a step despite the intention to do so. So imagine you're trying to move and suddenly you just freeze at that moment. It's quite scary, very anxiety inducing. And the problem with studying that behavior is when they come to the clinic and we're telling them, hey, can you show us this freezing? They're not going to freeze on cue. They often say, okay, I'm freezing due to a specific problem, like going through a doorway, and etc. So since we can't go to their home, we're trying to bring home to them. So what we're going to see is this patient who complains about freezing when he's trying to go through a doorway. And what we designed is, for this presentation here, is that we designed a space where the task for them is to walk through this narrow doorway that we could kind of control and systematically induce over and over again for them to study, okay, when they do freeze, what's going on in the brain. So on the top left corner is the head-mount display view coming from the MetaQuest Pro that they're wearing. Here is me and him walking through that doorway in real life. Obviously, we're not going to put a real doorway there, so they're not going to run into it, obviously. Here is a motion capture. We're tracking the body movement using reflective markers, and you're going to see their lower body movement as they walk through the space. And just bear with me real quick. So on the bottom here is a stream of data that's coming out. IEEG is intracranial data coming from the basal ganglia. The normal EEG here is the surface EEG cap that we're recording from a 64-channel EEG cap system on top of their head. The freezing index is a value we derive from the motion from their lower legs. And I could dive that into deeper if you're interested. Is we're using their body movement to predict the moments when they do freeze. And here's another view of inside the hallway. So when I hit play here, so they're walking, we're recording, and they see this doorway. Obviously, now they need to adjust their body and navigate through that. And he did that successfully. And then he turns into this hallway, and now he had to walk back through that doorway. And it's at this moment, he can't move, he can't take a step. And he's struggling, he's trying to get out of it, and finally he gets out of it. So I'm just gonna replay that real quick. And it's these moments here. This has never froze on me before. Sorry, guys. Yeah, okay. Yeah, and it's these moments right here where our job is trying to decode that signal out and see, okay, so what's happening at that brain when they're able to successfully go through the doorway versus those moments that they're unable to. And we're trying to dive into machine learning, etc., to help us decode that. And this is not a one-size-fits-all thing. So we will have patients come and they don't respond to doorways, right? They're completely fine with doorways, but they complain that when they're outside, that's when they freeze. So the next one I'm going to show you is one we're currently being built, and is a street crossing scene where a lot of times patients will report that they're out and about, and when there's people coming in, especially going around UCLA, all these kids are on their phones and they can't, a lot of stop and goes, and no one's like looking at them, and there's navigators, and they get stressed out. So for us, all right, we'll bring the stress to you in a control setting that we could, kind of monitor for safety, but also repeatedly study this, right? So here is a patient looking at the VR scene here. There's cars coming in, they're stopping, and the goal is to cross the street when the light, the pedestrian light comes on. And their job is to, assess the opening when the avatars diverge and make the correct, estimation and decision to cut through that. And not only we're studying navigation here, but we'll also study when they do freeze, what's going on. And when they're successfully able to navigate that, what's going on there too. And the talk's quite brief. This is my showcase about kind of the study we're doing in our labs. And we're also looking for help regarding to building VR scenes. So we use Unity, we use Unreal, and we do have VR programmers. Our studies are funded, and a lot of times we're just kind of looking at for perhaps master's students, undergrads, to help us to kind of upkeep the scenes. Just move the objects around, checking everything runs. Maybe do some if-else statements, etc. But yeah, thank you everyone for your attention today. Appreciate that.
Yeah, thank you so much. I think Tanvi is next. We do have a little bit of time for questions. We're running ahead of schedule, so if anybody has questions for Leo too. Yes, we've got 2 questions.
Where do you get a 64-channel portable EEG? Is that really a portable unit?
Yes, yeah, it's called, so this new company called M-Brain Train, and they just came out last year with a 64-channel. So the question was, is there a portable EEG system? As you imagine, it's a lot of wires, a lot of, the amplifiers are quite big to really bring out those signals. But there is a new company, relatively new company, that came out with a Bluetooth 64-channel EEG cap system, which we're using. It always sounds good until you're actually doing the recording. There's issues we had to trouble solve at all times, but it's getting the data through. And it's still quite heavy. It's probably like 8 ounces. They still have to wear a little pack in the back of their head, but it's better than the traditional huge backpacks, etc. Yeah. There's another question.
And I think there was one more question.
Take the mic. Why not? I had a question. I couldn't help but notice the irony of the video stopping when you're doing a study of people stopping at entryways. And I guess I had a question about like technical glitches and how you onboard your subjects to using, both the weight of a VR system as well as the various kinds of recording devices. And I guess I just imagine the disorientation that I've had even just introducing family members to VR spaces. And so I'm curious about what that looks like or how you think about, the technical glitches that these subjects encounter.
I'll grab more mics out of the back.
No, absolutely, it's a great question. Because we're dealing with patients, everyone's so individualized, and it really, nothing ever goes according to plan, but everything works out in the end. But we to answer one part of the question, to accommodate them, to get them to be accommodated to the scene, usually it takes about 20-30 minutes of just talking them through it while they're wearing the headset and having them walk, especially when you're walking in VR because you can't see your body. There's a kind of a confusion, disconnect with that. And studies have shown that when they are walking in VR, they actually take even shorter steps. And we have done study to see how we could attenuate those effects. And I think a lot of it is depth cues to make sure they could understand like where distance relative is when they're in the scene, but also just building that rapport and making them feel comfortable once they start with that. And then, yeah, there's always issues with, when you're dealing with multiple equipments, computers, we kind of troubleshoot as we go on, kind of situation. Yeah, thank you.
Great, thank you so much.